Alright, so in this problem we are told that we have a homogeneous disk of mass m and outer radius r, which rolls without slipping on a rough horizontal surface. We're told the spring, having a stiffness of k, is attached between the disk center at O and ground, as shown in the diagram. And we're at x to describe the position of point O, where the spring is unstretched when x is equal to 0. In this problem, we're asked to find an equation of motion for the disk in terms of the coordinate x, to find the particular solution of the equation of motion, and also to determine what the amplitude of the response given a certain excitation frequency, and determine whether this response is in phase or out of phase with the forcing. So in this regard, what I'll do is I'll start by drawing a free body diagram for this system. And if I do so, I'll note that if x is positive to the right, that I can have an mx double dot also positive to the right, and to be consistent, since I'm rolling without slip, I'll have some I about 0.0 times theta double dot. And in terms of forces, if I move to the right, I'll have a spring force pulling back of magnitude kx. I will have the weight of the disk, which is mg. I'll have a normal force between the disk and ground, and I'll have a friction force. I'll also, of course, have the applied harmonic forcing given here to be f of t. Now, the way I'm going to develop the equation of motion in this case, at least the simplest path I can do, is to choose to sum moments about point C, and I'll do so in a clockwise positive sense to be consistent with my notation in my free body diagram. And so I'll say that sum moments about point C is equal to the mass moment of inertia about point C times theta double dot. Now, if I do that, I can go ahead and sum moments. And in this case, I'll note that the only forces that create a moment about C are the spring force and the applied force. So I'll have minus kx times its moment arm length, which is r, plus f of t times r will equal, in this case, I about c times theta double dot. Now I can help myself out here a bit by noting that I about c is equal to I about O plus mr squared by the parallel axis theorem. And then if I simply note that I have a thin disk about its center of mass is 1/2 mr squared, I can note this is equivalent to 3/2 mr squared times theta double dot. Now at this juncture I would probably do two things. The first thing I would do is cancel out the common r that appears in this equation. And the second is to note that by kinematics x is equal to r theta, and by differentiation x double dot is equal to r times theta double dot. This, of course, means that in my previous equation up here, I can rewrite this as 3/2 times m times x double dot. And so if I now rewrite this equation of motion in standard form, I will have that 3/2 times m times x double dot plus k times x will equal f of t. And that'll give me my final equation of motion for this system. Provided, of course, where f of t is given by some f naught times sine of omega t. And let's go ahead and denote that as our equation of motion. So now that we have that, so of course we want to find the particular solution to this problem. And so let me add a quick page here in my notes to help us out with the length. And so what I'll note is that if we want to find the force response of the system, which is what we're asked to find, the particular solution, that x sub p of t can, generically speaking, be written as x sub p of t is equal to a times the cosine of omega t plus b times the sine of omega t. Of course, this means that xp double dot of t will be given by minus a times omega squared times the cosine of omega t minus b times omega squared times the sine of omega t. If I take both of these results and plug it back into the equation of motion, I'll get something here kind of tidy. Namely, I'll get that 3/2 times m times minus a omega squared times the cosine of omega t minus b times omega squared times the sine of omega t plus k times, in this case, a times the cosine of omega t plus b times the sine of omega t will equal f naught times the sine of omega t. I can now pull out like trigonometric functions, noting that the cosine and sine functions are independent of one another. And so if I look at whatever is multiplying cosine of omega t, I'll simply have that minus 3/2 times m times a omega squared plus k times a is equal to 0, which of course means that a has to be 0. And if I look at coefficients multiplying sine of omega t, I'll have that minus 3/2 mb omega squared plus k times b is equal to f naught. And the latter, of course, gives me that b is equal to f naught divided by quantity k minus 3/2 m omega squared. What this means is that my particular solution is given by x sub p of t is equal to f naught divided by k minus 3/2 m omega squared times the sine of omega t. Now in this problem we're asked to find the amplitude at a particular value, and so if you want to find that amplitude, we sometimes write as x sub p as a function of t, you're simply going to pull off here f naught divided by k minus 3/2 m omega squared. And to determine whether or not we're in phase or out of phase, what we would typically do is we would evaluate the excitation frequency and compare it with the natural frequency. So if we go back to the equation of motion here, what we would see is that the natural frequency in this problem is equal to the square root of 2k divided by 3m. And we would simply see if omega is less than omega n or omega is greater than omega n. And this is the question one needs to answer. And so once we determine that, we can actually get an answer, because if omega is less than the natural frequency, we'll be in phase, and if omega is greater than the natural frequency, we'll be out of phase. And if you happen to be the case where omega is equal to omega n, you'll be have a 90-degree phase difference. And so you can plug in your numerical values here, check your amplitude, check your frequencies, and get a nice tidy result. I wish you the best of luck as you do so.